He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Kia ora and a big hello and welcome to Elemental from RNZ. We are marking 150 years since the publication of the periodic table by Russian chemist Dmitry Mendeleev. I'm Alison Ballins.
And I'm Allan Blackman from the Auckland University of Technology. And since we're doing this alphabetically, and since this is episode 94 out of 96, we are in the Ys and closing in on the end of this adventure. But we aren't quite there yet. So last episode we looked at Ytterbium, and this time we are considering the very similarly spelt Yttrium.
Both, of course, named after the famous, chemically speaking, Swedish village of Ytterby. Names that look very similar, but are they similar in a chemical sense, Alan?
Well, before I answer that question, we need to do the vital statistics. Okay, so as usual, the elemental symbol for yttrium is Y and the atomic number is 39, which puts it, as we're going to see, in the second row of the transition metals, but we'll talk more about that in a minute. So when you consider the prolific elemental legacy from Ytterby, it is rather ironic that the single non-lanthanoid element yttrium did in fact spawn so many lanthanoid elements.
Explain.
So, well, the mineral yttria was discovered in 1787 near that town of Ytterby in Sweden, and 7 years later in 1794 it was proposed to be the oxide of a new metallic element, which was first isolated in pure form in 1828. So yttria was then shown to contain oxides of, in fact, 8 new elements, 7 of which are lanthanoids, which then obviously had to be isolated torturously.
I know how this goes now.
So these new elements were, alphabetically, of course, dysprosium, erbium, holmium, lutetium, terbium, thulium, and ytterbium. And that's 7 out of the 15 lanthanoids whose discovery was spawned by the discovery of that one piece of rock.
Wow.
Plus scandium, which, as we said back in episode 73, is a transition metal. So, despite its origination story being so tightly tied with the Ytterby lanthanoids, yttrium itself is also not a lanthanoid. It's the first element of the second row of the transition metals, and like its upper neighbour scandium, doesn't really behave like a quote-unquote normal transition metal.
All these things that don't behave normally. Now, we mentioned yttrium in passing in episode 85 when we were waxing lyrical at my behest about thorium and camping lantern gas mantles, since yttria has replaced thorium due to concerns about its radioactivity. What else do we use yttria for?
Well, addition of metallic yttrium to cast iron makes it more ductile, while alloys containing yttrium are used in cutting tools, bearings and jet engines. And also, yttrium has got a massive affinity for oxygen, and it is used to deoxidize metals such as vanadium.
Excuse me? Deoxidize?
Well, you know, like it says on the bottle, take oxygen away from, shall we say, or remove oxygen. So that's an especially important facet in steelmaking, but yttrium is used, in fact, as I say, to deoxidize vanadium pretty much specifically. It can take the oxygen out of that very nicely.
Thank you for that simple explanation, as you were.
Okay. So, yttrium oxide, or yttria, which has the chemical formula Y2O3, was used in the old cathode ray televisions, along with europium as part of the red component. And on this theme, yttrium finds significant use in lasers nowadays, particularly YAG lasers. And YAG stands for yttrium aluminium garnet. And we talked about some of these in the neodymium episode. And in fact, what we find is that some YAG lasers are in fact capable of cutting through metal. Quite powerful beasties, those. However, if we were to pick one thing that yttrium is most famous for, I would say that its crowning glory is its presence in a series of compounds containing yttrium, barium, copper, and oxygen. And these compounds, of which YBa2Cu3O7 is the most well known, are superconductors at liquid nitrogen temperature.
So why is this important?
I was hoping you would ask that, Alison. Okay.
Take it away.
So, superconductors. Why are we interested in superconductors? Well, it's been estimated that around about 6% of all generated energy is lost in transmission through power lines as heat. And that's quite a bit when you think about it. This energy is lost because power lines have a resistance to the flow of electricity. Now, superconductors, on the other hand, have absolutely no resistance to the flow of electricity. And what this means is that no power will be lost from superconducting transmission lines. So hopefully you can see why superconductors are a very big deal. Mm-hmm. Now, problem number one. Until the discovery of the aforementioned YBa2Cu3O7, and for shortness' sake, that is often called the 123 superconductor, so we might call it that from now on.
Oh, we like that. The 123 superconductor.
Until the discovery of this 123 superconductor, materials had to be cooled pretty much to liquid helium temperature, and that is below negative 269 degrees Celsius before they became superconducting. So that's pretty cold and also pretty expensive as well. Now, the much, much cheaper liquid nitrogen temperatures, and liquid nitrogen boils at minus 196 degrees Celsius, needed for the 123 superconductor, started a revolution in this area, which in fact began with a Nobel Prize for the discoverers of a closely related compound.
Well, they talk about high-temperature superconductors, and I do have to say that high temperature is a relative thing, since I don't count about minus 200 degrees as a high temperature. But with that off my chest, there's a really good New Zealand connection to high-temperature superconductors, isn't there?
Yes, indeed there is. So the Kiwi pair of Jeff Talon and Bob Buckley have been at the forefront of high-temperature superconductor research since its inception in the late 1980s, especially in efforts to make superconducting wires. And in fact, these two won the first Prime Minister's Science Prize in 2009.
Heroes. They are great scientists.
Absolutely.
Interesting yttrium fact, please.
Okay, so here's one for you. There appears to be up to 6 times the amount of yttrium on the moon as there is on the Earth.
Of course there is. And I'm sure all those companies eyeing up the moon for future mining potential have that in mind. And on that lunar note, that's us for this episode. Head to rnz.co.nz/chemistry to check out all the episodes that trace their discovery to Ytterby, or find them all at RNZ Elemental on your favourite podcast app. We're back next time with zinc, but until then, cheerio from me, Alison Balance.
And me, Allan Blackman. Mā te wā.